coming up, why memory is the next big unlock in AI evolution and what makes agentic systems more than just smarter models. So it's one thing for LLMs to sound intelligent, but what happens when they start acting with memory, purpose, and adaptability? Welcome to GenAI Revolution, the podcast where we dive deep into the evolving world of generative AI and agentic systems. I'm your host, Jothi Moorthy. Each episode, we unpack the forces driving innovation in the architecture and applications of intelligent systems and have peer-to-peer conversations with thought leaders moving the space forward. I'm thrilled to welcome Sireesha Ganti, a CSM architect and technical specialist at IBM. Sireesha has extensive background and expertise in working with clients across multiple domains, implementing and designing solutions for digital transformation. She specializes in generative and automation technologies and their practical applications, combining her passion for learning with technical writing and solution design and implementation. Sireesha is currently driving AI adoption, application modernization, and business automation for enterprise clients. So we'll be exploring the technical evolution of these systems, diving into what's emerging beyond traditional LLMs, and reflecting on how memory, anatomy, and modular architectures are reshaping intelligent workflows. Let's jump in. So before we dive in, Sireesha, welcome to this show. I'm glad to have you here.
Hey, Jothi, thank you so much. I'm really excited to be in this conversation today.
All right. So I love how you describe LLMs as cognitive engines in your article. It reframes how we think about these models. Can you walk us through that idea? What makes this shift meaningful in the evolution of AI?
Yes. So understanding LLMs as the intelligence of an agent or the cognitive engine of an agent is critical. The LLM functions as the brain module for the agent for two main reasons. First, the LLM helps the agent with storing and memorizing knowledge. And second, the LLM undertakes critical functions like processing information and making decisions. And it can perform activities like reasoning and planning and also cope well with unseen tasks. And that's how it exhibits the intelligence of an agent. So this image that we'll be sharing, it captures the topology of how LLM acts like a brain for an AI agent. You will see that there are the knowledge and memory components. Next, there is the natural language interaction component, which provides the AI agent this ability to communicate effectively using the natural language and plain English, for example. The brain module first receives the information processed by the perception module. Then it turns to memory and retrieves the knowledge that it has stored. This helps the agent in creating action plans, in reasoning, and in making informed decisions. And the brain module sometimes also memorizes the agent's past behaviors, thoughts, and actions in the form of vectors and other data structures. It can also update its knowledge and also use it in the future. One unique thing about LLM-based agents is that they are good at adapting to unfamiliar scenarios. And it happens in two ways. First is called generalization, which is basically the LLM's ability to apply what it has learned from specific examples to new and unseen situations. So, for example, if an LLM is trained to recognize dogs in images, it is able to recognize a dog in a brand new image, which this LLM has not seen before, regardless of the dog's posture or the background against which the dog is located. The second is called transferability, which is the LLM's ability to take the knowledge learned from one context and apply it to a different but related context. So, for example, if an LLM is trained to learn and play a particular type of game, then it might use this knowledge and memory to learn a completely different game with somewhat similar rules. So you can see how LLMs do all the heavy lifting of thinking and reasoning when it comes to AI agents. And that's how they function as this brain module for agents.
Yeah, that's a really helpful breakdown. The brain analogy really helps crystallize how large language models are becoming integral to perception, memory, and decision making inside agents. You touched on context and reasoning, and that naturally brings up the human comparison. How do you see LLMs mirroring or diverging from human cognitive processes?
Yeah, so let's take a look at some similarities between the LLM and human cognition. First, the LLM excels at recognizing patterns in textual data. The LLMs can predict the next word in a sentence based on the context that is provided to them. Human brains are also experts at recognizing patterns in language or in visuals or in social interactions. As human beings, we use this ability to recognize patterns and make predictions about the future. Then, LLMs also rely heavily on the context to generate meaningful responses, coherent responses. So, if asked about the climate and the weather, the LLM will provide relevant information. And human beings also respond appropriately in conversations, keeping the context in mind. In fact, our responses are heavily influenced by our knowledge, our experience, and overall context of that situation that we are in. Now, when it comes to differences between LLMs and human cognition, it comes down to two important things: how we learn and how our intentions and consciousness plays a role in the process of learning. So when it comes to learning mechanisms, we know that the LLMs train on massive amounts of data during the training phase until to a point where the model converges and the prediction errors are minimized. So this is clearly a data-driven process and does not involve experiential learning of any form. Humans, on the other hand, learn through a combination of experiences, social interactions, and also inputs from our senses. Then there is also this influence of emotions and motivations on our learning process. So it is not based just on the sensory inputs, but instead it is based on a variety of other factors. The human brain is constantly optimizing and adjusting the effects of these external other factors. Next, the LLMs also differ in that they lack consciousness or self-awareness. LLMs simply generate responses based on algorithms and training data. Human beings, however, have intentions, goals, and most importantly, an awareness of the self. We are driven by these very factors. So here we have LLMs and humans that are two very similar yet vastly different and very highly complex entities.
Yeah, so what you said about pattern recognition really resonates. It's fascinating how both systems rely on context, but human cognition draws from so many more layers: emotion and intention, self-awareness. So that distinction becomes so important when we talk about applying these systems in the real world. So let's dig into that. So what kinds of problems are these LLM-powered agents naturally well suited for?
So LLM-based agents have this unique ability to enhance efficiency and improve the overall decision making, which are the two core things that almost every enterprise in every domain wants to achieve. The applications are endless in customer service or customer support, in data analytics and process automation, in recommendation systems, fraud detection, human resources, and there are so many more examples, right? So, for example, in customer support, the AI agents can handle customer inquiries, resolve customer issues, and create support tickets. Ultimately, the agents are reducing the workload on human agents and improving the response times. In data analytics or data analysis, for example, the agents can analyze large, massive data sets to uncover trends, generate reports, and provide actionable insights. Agents are helping businesses make data-driven decisions. In process automation, the AI agents can automate repetitive tasks such as data entry, scheduling, inventory management, etc. And agents can help increase efficiency by reducing the risk of human error in process automation. Then there are recommendation systems. Here, the AI agents can analyze the customer behavior in order to provide personalized product recommendations. And this will help enhance the customer's shopping experience and, of course, boost sales and revenue for the enterprises. In supply chain optimization, Agents can optimize the supply chain operations by predicting demand, by managing inventory levels, and in identifying potential disruptions to the process. In human resources, AI agents can assist with recruitment by screening resumes, by scheduling interviews, and even conducting initial interviews, and basically streamline this entire process of hiring. So you can see the possibilities are so many, and these are just a few that are coming to mind right now.
Yeah, I'm nodding along because those are exactly the areas where we see momentum building, like structured workflows, large data sets, and personalization. But as we know, with more complexity comes more constraints, right? So, what are some of the current limitations you're seeing in deploying these systems efficiently?
Yep. So this is where the things start getting tricky. And that is because there is tons of active research that is going on in order to stretch the capabilities of agents and in order to get around the limitations. So, for example, take security vulnerabilities. The AI agents can be susceptible to a variety of security threats, including prompt injections and adversarial attacks. This can lead to unauthorized access, it can lead to data breaches, and the manipulation of the agent behavior. Then there are limitations that are inherent to LLMs themselves. For instance, bias and fairness, where the LLMs can retain biases from their training data, and that leads to unfair or discriminatory outcomes produced by the LLMs and therefore produced by the agent. LLMs can sometimes hallucinate, and that can cause the AI agents to generate incorrect or nonsensical outcomes. And then we have the data privacy concerns. Handling sensitive data requires very stringent data protection measures. AI agents must be designed to comply with the data protection regulations in order to avoid legal issues and protect user privacy at the end. Advanced agents are highly autonomous, and that raises questions around ethics, around accountability in case things start going awry, around transparency of how and why the agent made certain decisions. And lastly, there are lots of limitations around resource and computational intensity that is required to run these agents.
So basically, we've got these systems with incredible potential, but also a number of open challenges like security, trust, explainability. So now I want to pivot into the evolution side of things. In your article, Beyond Traditional LLMs, you talked about how we are moving past conversational architectures. In your article, Beyond Traditional LLMs, you talk about how we're moving past conventional architectures. What defines this next generation of agentic AI in your view?
So AI agents face many challenges that, like we discussed before, in terms of performance, in terms of accuracy, computational and resource needs, etc. And these challenges highlight the need for ongoing innovation in order to ensure that agents are both effective and efficient. And that is exactly what defines the next wave of evolution of traditional LLMs. Also, as agents execute more and more complex workflows and tasks, the computational resources that are required for training them and also at the time of inference grow exponentially. And this means more GPUs and more data storage, and all that results in more cost. Similarly, accuracy starts to take a hit when agents must implement workflows with multiple steps, or when agents have to maintain context and memory in interactions that happen over a long period of time. Such scenarios, with conventional LLMs, the agent can lose track of the full context, the agent can misunderstand interactions or instructions, and ultimately fail at the task at hand. So most of the innovation that is happening currently is directed at addressing these specific aspects.
Yeah, that perspective really helps set the stage. What stands out to me is how we are no longer just building better models, we are building more capable systems, one that can adapt, collaborate, and extend themselves. So, what capabilities do these agentic systems have that weren't possible with earlier AI approaches?
The biggest benefits that we are seeing are efficiencies in resource and computational needs. For example, there is a powerful machine learning methodology known as mixture of experts or MOE, where the LLM architecture itself is modified to realize some of these benefits. The MOE mechanism enhances the decision making and performance in LLMs and by extension in LLM based agents. In this mechanism, the feed-forward network layer of neurons inside the transformer architecture of the LLM is modified either partially or fully with specialized neural network layers known as experts. And these experts, they specialize in processing input tokens related to a particular domain of knowledge, like language and grammar, or punctuation, or conjunctions in articles, or verbs, or sometimes maybe they specialize in mathematical operations like counting numbers and calculations. Or they may also specialize in visual descriptions like color, spatial positioning, etc. So the experts become specialized in handling specific types of data or input tokens during the training period of the LLM. So now, by including these experts into the LLM architecture, the capabilities of LLM itself are enhanced in significant ways. It is so cool, but let me explain with an analogy here. Consider a scenario of a large library where several specialized librarians are available, and each librarian is an expert in each subject area like history, English, geography, math, etc. And if you have a question on history, only the history expert librarian is consulted and none of the other librarians are consulted. Alternatively, instead of all librarians huddling to answer every single question that comes in, only the relevant librarian gets approached for each question. And this introduces sparsity into the process, which also makes it very, very efficient. Something very similar to this also happens when LLMs are enhanced with MOE approach.
Yeah, so that framing about scaling constraints and interaction complexity, it's so important. Once we start talking about multi-step tasks and memory retention, the foundation really needs to shift, right? So you also wrote about mixture of expert models. I find that part especially intriguing. Can you explain how organizations are implementing MOE in advanced AI agents today?
Yep. So MOE approach is widely used in many agentic AI applications simply because of its ability to enhance performance and efficiency by implementing these specialized neural networks, or also known as experts, in their LLM architecture. So for example, in healthcare medical diagnostics, MOE models can specialize in analyzing different types of medical data, including imaging and genetic data, and provide more accurate diagnosis and treatment recommendations to the patients. Agents built to address specialized healthcare workflows can also provide personalized treatment plans to the patients. MOE LLMs are also used in recommendation systems to provide suggestions based on user preferences and also user behavior. And that enhances the relevance and accuracy of the recommendations that are provided by these systems to the users.
So it really does feel like we're entering a more composable, efficient phase of AI with expert models, dynamic routing, and purpose-built layers. Let's keep going down that path. To set the next segment, I want to shift the conversation towards something foundational, like memory. It's one thing to build smarter models. It's another to help them retain recall and evolve over time. So one of the biggest constraints we've faced with LLMs is memory. You've explored this deeply in your article on MemGPT, and I found it fascinating, actually. Can you walk us through how the MemGPT framework works?
Yes. So let me explain this idea behind the MemGPT framework with an analogy. Consider a scenario where you want to capture a scenic view using a camera. The camera's lens determines how much of the scenic view you want to capture in your photo, right? A wider lens allows for more meaningful and relevant pictures, whereas a narrower lens focuses on specific details and might actually miss the larger picture. Now, when it comes to language models that use the transformer architecture, the context window determines how much input information the LLM can consider, when generating the responses during the inference time. So a larger context window allows for more comprehensive and relevant outputs, while a smaller context window focuses on specific details, but it may also miss the broader context. And you can extend the context window by increasing the number of input tokens, but that method has its own limitations. MemGPT or Memory GPT is an agent design framework that addresses this limitation in a beautiful manner. It is actually inspired by the popular virtual memory technique used by operating systems in traditional computing. So, virtual memory allows a computer to use disk storage as an extension of random access memory or RAM. This enables the users to run programs that would take more memory than the physical memory would allow. And that creates this illusion of a large main memory available to the user. Similarly, the MemGPT framework enhances the LLM so that it can manage its own context window and also manage the data that is stored within and outside its context window. So there are these three key ideas underlying the MemGPT framework. First is memory management, which is accomplished by LLM operating system that moves the data in and out of the context window of an LLM in order to manage its memory. And this LLM operating system is usually another LLM that manages the data and also captures the state of the agent, among many other things. So remember that to capture the state of an agent means to store all of the agent memories, the message history, and the tools used by the agent, and store them into a backend database. And this database can be accessed, it can be updated as needed. So that was a memory management component of it. The second key idea that underlies MemGPT is this concept of memory hierarchy. Here, the LLM operating system splits the agent memory into two parts. One part is the in-context memory or the core memory. The core memory in MemGPT framework includes agent's own persona, the user information, among other things. And because the MemGPT agent has self-editing memory, it can update its own persona over time. And the agent persona is same as your system prompt. The MemGPT agent can also update the user information as it learns new facts about the user during the session and also from the context window. And there is this other part called the out-of-context memory or the archival memory. And this is the same as the external database that I mentioned before. And remember that this archival memory is typically connected to a MemGPT agent that is backed by a vector database. And this vector database can be replaced by a traditional relational database, or it can be also a rudimentary CSV file for storing this that is supposed to sit outside of the context memory. So there is some flexibility there. And lastly, the MemGPT agent moves data in and out of the core and archival memories using a variety of tools. And it is actually really fascinating how the MemGPT framework functions as a whole.
Right. Yeah, I really appreciate how you use the virtual memory analogy. So the connection to OS level thinking helps ground it in something familiar, right? So, and the idea of an LLM operating system managing state and memory hierarchy is powerful. It kind of mirrors how humans function too, right? Like switching between working memory and deeper recall. And the fact that these systems can now structure their own memory access is kind of huge. So when AI agents have enhanced memory capabilities like this, what new use cases or behaviors become possible?
So enhanced memory opens up a world of capabilities for agentic systems. Agent memory, it plays a direct role into agent's accuracy and its ability to hold long-lasting interactions and conversations with users. In the customer service AI agent example, if a customer previously mentioned their preference for a specific product, then the MemGPT agent can actually recall this information from archival memory or the long-term memory database during the future conversations. And then it can offer tailored recommendations to this customer in order to improve the overall user experience. And not only that, the agent can update, remember, and retrieve if the user preferences change along the course of these long-term interactions. This is the most common use case. And other applications of this lie in areas such as document analysis, summarization, generation of extremely lengthy legal or medical documents.
Wow, that example of remembering user preferences or maintaining state across long conversations kind of like really stood out to me. It makes sense these agents feel more personalized, more adaptive, and it opens doors to more complex and longitudinal interactions that were a little too brittle before, right? So we've covered a lot of ground today, from how LLMs act as cognitive engines to what's evolving in modular architectures to memory innovations like MemGPT. So Sireesha, thank you so much for walking us through these ideas with such clarity and depth. One key thing I'm taking away is that agentic systems aren't just smarter, they are becoming more structured, more selective, and more capable of adapting over time. And memory, that's kind of the real hinge point for long-term intelligence, right? So thanks for tuning in. I'll include links to Sireesha's articles in the show notes, including Mastering the Art of Using LLMs as Cognitive Engines and Agentic AI Unleashed. Highly recommend checking these out. In our next episode, we'll be continuing this thread, looking at agent efficiency, web integration challenges, and ethical considerations. Thank you, Sireesha, for joining us today. And thank you to our listeners for tuning into GenAI Revolution podcast. So until next time, I am Jothi Moorthy. This is GenAI Revolution. Thank you.
Thank you.